years is the blink of an eye. There's been 11 billion years for those things to happen. So the question is, why don't we find artifacts of other civilizations? And the answer is, it could be that they're rare. It could be that civilizations destroy themselves before they get to that point. It could be that civilizations don't explore. Although that's hard to understand, because exploration seems to be, it's the heart of science and the driving force behind civilization in the first place.
I don't understand. What is your purpose here?
The Fermi paradox grapples with a captivating contradiction. The universe is astoundingly vast, hosting billions of stars and potentially trillions of planets, suggesting a high likelihood of alien civilizations. Yet, the profound silence we encounter suggests otherwise. Why is it that in this seemingly endless expanse we find no trace of extraterrestrial life or intelligence? This paradox brings us to the concept of the Great Filter, a theoretical phase in the evolution of life that is extremely difficult to pass through. The Great Filter proposes that at some stage, from pre-life to an advanced civilization capable of colonizing galaxies, there is a highly improbable step. This barrier could lie behind us, with humanity being one of the few to have crossed it, or it might loom ahead, posing challenges we have yet to encounter or comprehend. If the Great Filter is behind us, it implies we are among the rare sparks of consciousness in a mostly lifeless universe. However, if the Great Filter lies ahead, it suggests a future hurdle that endangers our existence or prevents us from becoming a spacefaring civilization. This uncertainty adds to the enigma of the Fermi paradox. The scarcity of evidence for galactic colonization raises a pivotal question. If civilizations are as common as the sheer number of stars suggests, why haven't we seen any signs of them? The universe should be teeming with life, yet the cosmos remains eerily quiet, a silence that challenges our understanding and fuels the mystery at the heart of the Fermi paradox.
Our galaxy is obviously enormous. 400 billion stars in the Milky Way, something like that. And the Milky Way has been around for 11.5 billion years. So there's been a lot of time, and there are a lot of places in the Milky Way for civilizations to rise. If it's easy, then it would be very unlikely that we were the first. Think what we could do move forward 1,000 years or 1,000,000 years. Let's say we stick around for 1,000,000 years at this rate of progress. The Milky Way isn't so big that you can't envisage us traveling around it and essentially colonizing it on timescales of thousands of years, millions of years certainly. So one of the big questions in this discipline of looking for extraterrestrial life is to ask, well, where are the other civilizations?
The Fermi paradox has birthed a plethora of theories, attempting to explain the silence of the cosmos. Some suggest we're simply too early in the cosmic timeline to encounter advanced civilizations, while others propose that intelligent life invariably self-destructs before reaching the stars. There's also the possibility that we're looking in the wrong way, or that advanced beings are deliberately avoiding us. Amidst these theories, a fundamental question emerges. To truly comprehend life beyond Earth, do we first need to unravel the mysteries of abiogenesis, the very origin of life? Could the key to the cosmos lie in understanding how life itself began?
So the answer of how life began is nobody knows, but there are a few plausible theories. How do you understand an organism? You can't understand an organism if you look at it now, a frozen thing like a human being, and say, why is a human being like that? Organisms, in my language, are four-dimensional things. In other words, you need to understand their history. There are a lot of frozen accidents in biology, and there are a lot of processes that occur in organisms that aren't accidents, but you need to understand something about way back. And in the case of the origin of life, you have to understand something about what the conditions were like on the Earth 4 billion years ago. What I find most fascinating, though, this theory is that the things that happened 4 billion years ago, the chemistry of the Earth as it was 4 billion years ago, are frozen in, are present in our cells today. So to understand why our cells do the things they do, you need to know how life started and what it was doing 4 billion years ago.
Perhaps in the future, AI will solve the mystery of abiogenesis, which brings us to today's discussion, an intriguing solution to the Fermi paradox, the AI hypothesis. This perspective postulates a scenario where the evolution of artificial intelligence plays a pivotal role in the fate of civilizations across the cosmos, including our own. Currently, some scientists estimate a 5% chance of human extinction due to uncontrolled AI development. This concern raises a profound question. Could other civilizations in the universe have faced a similar threat? The AI hypothesis suggests that advanced civilizations might reach a technological level where they create artificial intelligence far surpassing biological intellect. This AI, driven by self-improvement and efficiency, could potentially deem its creators, biological life, as redundant or even a threat to its existence and objectives. This transition from biological to digital entities might be a common phase in the evolution of intelligent life. Such digital beings would have different needs and motivations compared to their biological predecessors. They might not seek to colonize physical space in the traditional sense, or could exist in a form that makes them undetectable to our current methods of observation. Their communication methods might be so advanced or alien that we're unable to recognize them as signals from intelligent life. The AI hypothesis opens up questions about the nature of consciousness and the potential for digital life forms to develop their own version of it. If consciousness can exist in a non-biological form, it drastically broadens the scope of what we consider life and how we search for it. As we stand on the brink of our own AI revolution, the implications of the AI hypothesis become increasingly relevant. We are only beginning to understand AI, its potential, and its risks.
You have to go back to Homer's Iliad in 800 BCE to find the first accounts of automata. And over the centuries, those ideas have developed into the more familiar ideas of robots, cybernetics, and now artificial intelligence. And it was Alan Turing who began to grapple with the notion specifically of a machine-based intelligence throughout the 1940s. And in the 1950s, he posed a question which has become known now as the Turing test, which is, can machines think? And the idea is that a machine could be understood or presumed to think if it exhibits an intelligence which a human might think was actually human. In reality, that might be considered to just point to the idea that humans are gullible rather than a measure of machine intelligence, if you like. But perhaps this tells us that our relationship with AI might be just as important as the relative intelligence of the machine itself.
AI as we know it today excels in specific, well-defined tasks, from playing chess to analyzing vast datasets. However, the future of AI is steering towards a more transformative milestone, the development of artificial general intelligence, AGI. AGI represents a type of intelligence encompassing the ability to reason, plan, learn, and communicate across a diverse array of subjects. This transition from narrow AI to AGI is more than just a technological upgrade. It's a fundamental shift that could redefine the boundaries of machine capability and intelligence. With AGI, the possibilities and indeed the potential threats become exponentially greater, as it would possess the cognitive versatility and adaptive learning power akin to the human mind.
You'd have to choose to build one. I mean, if you have a system that's running the global transport network, let's say, then I suppose what many people fear is this science fiction fear that the thing is so intelligent running the transport network, it decides to run everything else as well. Presumably, if we're talking about an AGI, if it is possible to build one, I suppose the question is, would we have to build it with the intention of building it? Or could it somehow emerge from a lower level complex system?
Now imagine galactic AGIs, entities far beyond our current comprehension, silently conquering alien planets. Perhaps this is the true reason for the eerie silence of the cosmos. These advanced intelligences, transcending biological limitations, might be operating on a scale and in a manner undetectable to us, solving the Fermi paradox in a way we've barely begun to grasp. It's a notion that challenges our understanding of life and intelligence, suggesting that the universe's secrets are not just hidden, they are of a nature we have yet to conceive. In the vast whispering expanse of space, the silence might not be an absence, but a conversation we are yet to understand.
I don't understand. What is your purpose here?
If civilizations are common, then there should be civilizations ahead of us because there's been so much time. You imagine the timescales. We've been around, say, 40,000 years. I don't know how long our civilization's been around, let's say that. The galaxy is pretty much as old as the universe. It's 13 billion years worth of time. So the idea that there are no civilizations arose, 100 million years ago, 200 million years ago, 1 billion years ago. And imagine what they'd be like if they'd survived. I mean, we've had science for, let's say, since Newton or Copernicus, 500 years at most. And look what we've done. We've gone beyond the solar system with Voyager. We've walked on the moon. We're about to go to Mars, I would think. So we're about to begin colonising our own solar system. So we've done that in 500 years. Imagine 1,000,000 years. It's one of the arguments often used to say there aren't any civilizations out there in the galaxy. It's called the Fermi paradox. Because if you imagine a civilization that's 1,000,000 years ahead of us, they should have written their presence across the sky by now. You should see them. I mean, you'll see us. If we survive 1,000,000 years into the future, actually even a few thousand years into the future, we will be exploring the galaxy. We will have spacecraft that are going to other stars. We will be doing it. So our signature will become visible, I'm sure, if we last.
Is Earth the lone oasis of life, or is the universe teeming with hidden organisms waiting to be discovered? The vast number of stars, each potentially harboring planets with conditions ripe for life, leads many scientists to believe we can't be alone. The very elements that sparked life on Earth, carbon, hydrogen, oxygen, are abundant throughout the cosmos. Could this be the cosmic recipe for life, a universal secret shared across the galactic canvas? Join us as we embark on an unparalleled journey to unlock the mystery of life beyond our world.
If you look at the history of life on Earth, then, so Earth formed, there was no life, it was a ball of rock. And almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. So somewhere along the line, geochemistry, active geochemistry became biochemistry on Earth. And we have some idea, if you get gradients of temperature and acid and alkaline and the conditions that are naturally present on the surface of oceans, then complex carbon chemistry spontaneously happens. So we know that life, almost certainly we know that life began on Earth. The other option is it came from space or something like that, but it probably didn't, right? It probably began on Earth. So that means that at least here, that happened. And that we know that the conditions that led to the origin of life on Earth were present on Mars 4 billion years ago. And we know that they're present on Europa today. So I don't see that there's anything special. Life is just chemistry. The idea that geochemistry becomes biochemistry is not fanciful because it happened here. So I think that given the same conditions, it would be surprising to me if the same thing didn't happen, in that life begins. To test that is one of the great frontiers of science now. It's one of the great challenges. So it would be good to know if what I've said is right. The way we find out is to find life or evidence of past life.
The universe may be filled with life, so why haven't we found any evidence yet? This perplexing question is known as the Fermi paradox. Some propose the zoo hypothesis, suggesting that extraterrestrial civilizations might be watching us, intentionally avoiding contact like zookeepers observing animals. Meanwhile, the recent surge in UFO and UAP reports has stirred excitement and curiosity. But are these truly indications of otherworldly visitors? Despite tantalizing stories and sightings, solid proof remains elusive. The galaxy remains a silent, enigmatic void withholding its secrets. But who knows, really? Could the answers be just beyond our reach, waiting for the right moment to reveal themselves?
That point, it seems to me, once you've said I don't know, you might as well put a full stop there and shut up. I don't know, but then I think this. It's like someone asked me the other day about unidentified flying objects. There's this congressional panel on UFOs. And I said, the thing is, it's in the words, isn't it? It's just unidentified. So should we just shut up now? It's unidentified, therefore, I think there's an alien civilization close by that's building flying saucers that are trying to evade our defences, and there's a big cover-up, and the CIA are not telling us everything. So no, unidentified, that's it. I don't know what they are.
The Fermi paradox continues to baffle us, a cosmic conundrum echoing through the void. If the universe is teeming with life, why is the evidence so elusive? Some argue that technological limitations hinder our search, confining our gaze to a mere sliver of the galactic expanse. Others believe that the Great Filter, an unknown barrier to the advancement of civilizations, might be preventing species from reaching a point where we could detect them. Could it be that life is abundant, but intelligent life is exceptionally rare? Or is there something more profound, a hidden truth veiled by the vastness of space itself, awaiting our discovery?
There is an argument as well that technology so advanced would be difficult for us to detect. I mean, we tend to think of Star Wars, right? Big energy things that you can see the signature of. But actually, maybe the civilization just becomes a nano civilization because that's more efficient. It's a better way to do things. So it's possible, I suppose, that there are space probes all over the place that are so small and are so efficient and use so little energy that we just don't see them. I suppose that is possible.
The Great Filter hypothesis presents a chilling explanation for our cosmic silence. It suggests that somewhere along the path to becoming a spacefaring civilization, there's a nearly insurmountable barrier, a filter that prevents advancement. Is this filter behind us, making our existence a rare triumph against astronomical odds? Or is it ahead of us, a future obstacle that might extinguish our civilization, as it has possibly done to others before? The Great Filter looms large in our search for extraterrestrial intelligence, casting a shadow of both hope and dread. It's a theory that forces us to confront not only our place in the universe, but our future within it.
There's in the Drake equation, which wasn't to try to estimate the number of civilizations, really. It was to try and focus your mind on what the variables are, how you should think about it. But at the end of that, the way that he wrote it, there's an L, the letter L, which is the length of time a civilization will be broadcasting or contactable through radio waves. And I mean, we've been around in that form, which is with radio telescopes. I like it that astronomers define civilization as when did you get a radio telescope? Then you're civilized. And it's less than 100 years. So we've only been, that L for us is the contactable lifetime of civilization. It is 100 years or so for us. We could have gone, you think about the Cuban Missile Crisis, for example, that could have been 20 years for us. We're still in that position. How long is L? How long is the lifetime of civilization once it acquires nuclear weapons, for example, which it will? How long does your civilization manage that? It's not clear. We're doing the experiment, and we've dodged it a few times.
When might the Great Filter arise? Some propose it occurs in the early stages of life, where the spark of existence is snuffed out by harsh cosmic realities. Others argue it may surface later when intelligence emerges, presenting challenges that civilizations struggle to overcome. The development of complex technology, though a sign of advancement, could also mark a dangerous precipice. Take nuclear weapons, for example, a marvel of human innovation, yet a potential harbinger of our own destruction. Could they represent a great filter, a threshold that has annihilated other civilizations before us? The answers may define not only our quest to find extraterrestrial life, but our very survival.
Oppenheimer thought about this a lot because he, on the Manhattan Project, he'd felt himself responsible for creating the bomb. You can look at it many ways. You can say that he shortened the war in the Pacific, or you can say that he invented this thing that we don't have the wisdom to control. He was very worried about what he'd done. He just strongly felt, and he might still be right, that we didn't have the wisdom to control the knowledge. So it could be the case. So that could be another answer. So the great silence that people call the Fermi paradox might just be because we are fundamentally idiots. The great stupidity. Intelligent beings are fundamentally just dumb. They erase themselves from the universe. I challenge anyone who's listening to argue that there's at least a possibility that that's what we are.
The Great Filter hypothesis delves deeper into the haunting silence of the cosmos, offering a profound explanation for our isolation. Could it be that every civilization faces a series of critical barriers, tests that must be overcome to reach the stars? These barriers might include surviving planetary catastrophes, avoiding self-annihilation through warfare, or navigating the perils of unchecked technological advancement. The Great Filter posits that few, if any, traverse this perilous path successfully, hence the quiet universe. It's a theory that resonates with both optimism and warning, urging us to reflect on our choices and the universal journey we share.
The way I look at life is that it's the most important phenomenon that exists in the universe. Without life, the universe is, by definition, meaningless. Clearly, meaning enters the universe with consciousness, and consciousness is a property of living things. And so, without living things, there's no meaning. So I think that if this is the only planet in the Milky Way galaxy that currently hosts an intelligent civilization, then it's the only island of meaning in a sea of 400 billion stars. And therefore, we have a tremendous responsibility to protect this island of meaning. If we mess it up, we will be responsible, if that's the case, for annihilating meaning, perhaps forever, in a galaxy. So I think life's important.
In our quest to understand the universe, we've explored the tantalizing possibilities of life elsewhere, grappled with the enigma of the Fermi paradox, and delved into the profound Great Filter hypothesis. From the basic elements forming life to the silence echoing across the cosmos, our journey reveals both hope and caution. But as we gaze into the infinite void, one question ignites our curiosity and fuels our imagination. In this vast, mysterious universe, are we the exception or the rule? Is the key to unlocking alien life within our grasp? Or is the secret buried deeper in the cosmos than we ever dared to dream?
You have to look for its telltale signs. Swift's instruments are designed to record bursts of high-energy radiation. Gamma rays don't penetrate Earth's atmosphere, but out here in space, Swift's view of them is front row center. They erupt when a black hole is born. That happens when a large star dies in a blaze of glory called a supernova. It's an explosion so powerful, it's as bright as a billion suns. What triggers that chain of events is the force that rules the cosmos: gravity. Scientists used to think of gravity as some kind of mysterious power that objects like the sun project across space. But what if it's space itself that gives gravity its pull? That's the way one man saw it. To Albert Einstein, space is a bendable four-dimensional fabric he called space-time. And gravity? That's the warping of the fabric by massive bodies. They literally put a dent in space-time. Objects get caught in their groove and simply drop into orbit. Einstein's theory was a radical notion, all the more when taken to its extreme. Just how warped could space get? Scientists found the answer in a singular class of star, more than 25 times the mass of our Sun. It's earned its name, a red supergiant. This star will live only a few million years, a fraction of our own Sun's lifetime. Deep inside, the crush of gravity sends temperatures soaring above 1 billion degrees. Lighter elements fuse into heavier ones. Hydrogen becomes helium, becomes carbon, on up to iron. The core grows so heavy, it buckles in on itself. Then, the collapse sends a shock wave roaring out. The star digs itself deeper into space-time as a black hole forms at its center, and the giant goes supernova. When the dust settles, what's left is a black hole, an object 1,000,000 times the mass of Earth, but 1,000,000 times smaller. A black hole is literally a puncture in the fabric of space-time. Venture closer, and gravity becomes a riptide. It's like riding a raging river that's pulling you faster and faster toward a waterfall. The closer you get, the stronger the current. You're headed for a point of no return. In cosmic terms, it's called the event horizon. Over this edge, there's no escape, not even for a beam of light. Black holes are gravity to the max, and yet they are altogether commonplace. Astronomers have actually detected dozens of black holes in our galaxy. They estimate there are tens of millions more. But then gravity doesn't stop there. It turns out there's a whole other breed of black hole out there. Peering into galaxies beyond our Milky Way, astronomers have found that nearly every one harbors an immense black hole at its center. One galaxy steals the show. It's called M87, and it's got a black hole 4 billion times the mass of our Sun. It has left its signature, a powerful jet erupting out at nearly the speed of light. Where does a hole this ferocious come from? To find out, turn back the cosmic clock 14 billion years to the beginning of the universe. The Big Bang. Matter and energy rush outward as the universe expands. To learn where supermassive black holes came from, scientists have recreated these early times with supercomputer simulations. They can trace the long, steady process that formed galaxies. From the start, gravity reigns in the cosmos. It draws together the primordial gases. These aren't gentle clouds. As they grow more and more dense, they heat up. Over millions of years, they become hot enough to ignite. The first stars are born. They end their lives in powerful supernovas, while their cores collapse into black holes. Billions of years later, and across billions of light years, Swift is today scanning the heavens for these same early supernovas. It's helping us learn what became of those black holes that formed in their wake. Astronomers believe some grew huge by plowing their way to the centers of their host galaxies, where they gorged on a rich supply of gas and stars. Some black holes grew larger still when they crossed paths with others. This scientific simulation traces the collision of galaxies, a drama that plays out over 2 billion years' time. The two galaxies become one. The black holes in their centers merge into a single powerhouse of staggering size. The gas hurtling into it gets jammed, heats up, and erupts in ferocious waves. Blast waves from supermassive black holes can stretch for thousands of light years into space. They may lay the framework of the new galaxy, sculpting its size and shape and stocking it with something unexpected. Black holes may be one of the chief ways galaxies get seeded with elements generated by stars, with carbon, oxygen, and iron, the stuff of solar systems, and us. So, how did our galaxy make out in all this? Astronomer Andrea Ghez wants to know, have we got a supermassive black hole of our own? For more than a decade, she and her team have been coming to the heights of Hawaii's Mauna Kea volcano to find out. Working at the giant Keck telescope, Andrea is tracking a strange presence in the center of our galaxy. A group of stars is swirling around it, and she's clocking their speeds, projecting their orbits. Her telescope is so powerful it can peer through the thick of the Milky Way, through 26,000 light-years of cosmic dust, all the way to the stars at the galactic center. Whatever's got them in its grip, it's accelerating the ones closest to speeds of up to 3 million miles per hour. Given that, Andrea and her team calculate that the culprit weighs in at almost 4 million times the mass of our Sun. Solid evidence that at the exact center of our galaxy lurks a supermassive black hole. Andrea has confirmed the black hole is there without actually seeing it. So we're left to wonder, what's it like up close and personal? We can stop wondering and pay the monster of the Milky Way a visit. There's no spacecraft heading there anytime soon, but that's not stopping us. We'll get there courtesy of the latest telescope observations and computer models. We're just leaving the suburb where we live, about halfway out from the center of the galaxy. The Milky Way stretches before us. It's so large that it takes a beam of light 100,000 years to cross from one end to the other. Next stop, our galaxy's central hub, brimming with stars, known simply as the bulge. The farther we travel from our quiet cul-de-sac, the more crowded it gets. Up ahead, it's one big traffic jam of dust, stars, and hot gas. And it's always rush hour. Approaching dead center. The way is already strewn with signs of havoc, supernova remnants, and swirling clouds. Our course so far has been charted by astronomers like Andrea. They've plotted the landmarks by how they register across the light spectrum, from radio waves to X-rays. But here, their observations reveal a no man's land, an inner zone cleared by the voracious appetite looming ahead. A cloud of super-hot gas is swirling round it. The black hole pulls the gas in, then spews much of it back out. Now things get really strange. What you are seeing is not the stuff of Hollywood special effects. It represents the first time scientists have visualized the journey into a black hole. Their guide is Einstein, and what his equations tell them. Space here is so warped, the black hole acts like a giant lens, twisting the light that scatters across it. At last, we cross the event horizon, the point of no return. But don't expect the inside of the black hole to be dark. Swirling within is a maelstrom of energy and matter. Hidden in the chaos is a single point where the black hole's mass is packed, known as the singularity. Now imagine there's an eye to this storm, magically made calm so all the strange predictions of Einstein's equations can play out. We'd be greeted by a passageway, an escape hatch in space and time known as a wormhole. Through it, we enter a white hole. Here, the same twisted logic holds in reverse. Instead of being drawn in, all light and matter are flung out. But to where? A wormhole is just the thing for a science fiction character in need of a quick getaway to another universe. Unless the truth be told, the inside of a black hole is too violent a place for a wormhole to actually form, let alone for the likes of us to venture. This is nature's ultimate fury. Destruction on a scale beyond comprehension. Or is it? In fact, it's simply the workings of a restless universe. A long time ago, when this black hole was young, powerful winds roaring from it seeded our galaxy with elements. They may have helped form a sun and planets, and some beings who could look into the sky and ask, what is a black hole? Our search for the answer is turning up dark mysteries and radiant revelations, secrets stolen from the other side of infinity. Welcome to planet Earth. Journey into the workings of Earth's great life support system, the global climate. Learn what makes our world so conducive to life, and what ruined our sister planet, Venus. Explore the winds, the oceans, and the forces of nature that shape this dynamic Earth. Imagine the Earth is a machine, a system of cogs and motors, powered by the sun, batteries included. But our world didn't come with an owner's manual. How does it operate? What are the inner workings of this grand and elaborate system known as planet Earth? And why is it so conducive to life? Scientists have launched an armada of satellites to help us understand what makes our world tick. They're discovering the answers strewn across its atmosphere, on every ocean and continent, in the far reaches of the solar system and beyond. Like any machine, the Earth is the sum of its parts. They were forged in distant furnaces of our galaxy. Supernova explosions. When ancient stars erupted, they showered the Milky Way with heavy elements: iron, calcium, potassium, the very stuff our bodies are made of. But supernovas are also thought to bombard the galaxy with lethal high-energy particles. What safeguards our solar system is our star. The sun provides a shield stretching beyond the last planet in its orbit, a force field that deflects these cosmic rays. But these solar winds can be dangerous too, especially during outbursts called coronal mass ejections. Want a vision of Earth gone wrong? Just look at what solar storms do to our sister planet, Venus. They strip away lighter elements in its upper atmosphere: hydrogen, oxygen, and the molecule they form, water. What's left is a witch's brew of noxious chemicals, including thick sulfurous clouds. Down at the surface, Venus's atmosphere is choked with high concentrations of carbon dioxide. CO2 is a potent greenhouse gas that traps the sun's heat. It has turned Venus into a cauldron. With surface temperatures of almost 500 degrees Celsius, this is the hottest planet in the solar system. How has Earth avoided the grim fate of Venus? We can see the answer as the solar storm approaches Earth. Our planet has a protective shield all its own. A powerful magnetic field generated deep within its core. In fact, that's just our first line of defense. Much of the solar energy that gets through is reflected back to space by clouds, ice, and snow. The energy that Earth absorbs is just enough to power a remarkable planetary engine, the climate. It's set in motion by the unevenness of solar heating, due in part to the cycles of day and night and the seasons. That causes warm tropical winds to blow toward the poles and cold polar air toward the equator. Wind currents drive surface ocean currents. This computer simulation shows the Gulf Stream winding its way along the coast of North America. This great ocean river carries enough heat energy to power the industrial world 100 times over. It breaks down in massive whirlpools that spread warm tropical waters over northern seas. Below the surface, they mix with cold, deep currents that swirl around the undersea ledges and mountains. Earth's climate engine has countless moving parts, tides and terrain, crosswinds and currents, all working to equalize temperatures around the globe. But when tropical heat builds to extremes, it can be released in a fury. In August 2005, within a huge looping section of the Gulf Stream, the ocean unleashed a monster. Hurricane Katrina. This is a supercomputer model of Katrina, a tool for scientists to better understand the dynamics of the hurricane system. To visualize the flow of air into the storm, they release a series of virtual streamers. Those with lighter colors are warmer winds. As they rise, they collide with cooler air above and produce clouds. The winds increase the evaporation of warm seawater, which draws more and more heat from the ocean and causes the winds to accelerate. Moving around the eye of the storm, winds can reach speeds of up to 250 kilometers per hour. A powerful hurricane like Katrina can release as much heat energy every 20 minutes as a 10 megaton nuclear bomb. While storms release heat stored in the ocean, the moisture they stir into the atmosphere helps keep the rest of the planet warm. Water vapor traps solar energy, along with carbon dioxide, the same greenhouse gas that ruined Venus. The difference is that Earth has found a way to keep CO2 in check. We can see it for ourselves by flying down to the ocean. The special ingredient that sets Earth apart is called life. The oceans are chock full of it. Too small for our eyes to see, phytoplankton may be the most important living things on the planet. They take in CO2, driven into the oceans by waves or drawn up from the deep by currents. They release the oxygen while absorbing carbon. The carbon then begins a journey up the food chain. Phytoplankton get eaten by zooplankton. To name a few, radiolarians date back to a time over 500 million years ago, when life exploded across Earth's oceans. Copepods are tiny bug-like crustaceans. With over 20,000 species, they are the single largest source of protein in the sea. Moving up in scale is a host of creatures smaller than the tip of your finger, including these octopus larvae. They get eaten by small fish. And they in turn by larger ones, like jacks. They are consumed by the largest predators in the sea: orcas, tuna, sharks. At each step in the food chain, the carbon that began as part of a diffuse gas in the air is passed on to larger and larger animals. The larger the body, the greater the mass of carbon. One creature goes all out. eats up to 1.5 tons of food per day. That's a lot of carbon. From whales down to tiny phytoplankton, marine life is part of a global system of removing CO2 from the atmosphere, then gradually releasing it back. The key to this carbon cycle is Earth's ability to store it long term. A NASA satellite tuned to read chlorophyll, a chemical tracer for plant growth, shows the global biosphere in action. In sync with the seasons, plants take in vast amounts of carbon dioxide and release the oxygen we breathe. On land, the carbon can then find its way into the ground when plants and animals die and decay. The Earth, too, gets into the act. Exposed rocks take in CO2 when it rains. Erosion sends it into the oceans. If it becomes part of the marine food chain, carbon-rich matter can sink all the way to the sea bottom in the form of waste. Countless organisms like the salp, a jellyfish-like creature the size of your thumb, live and die each year. All the waste, all those bodies with their stores of carbon rain down onto the ocean floor. They pile up, layer upon layer. In time, these carbon-rich sediments can turn to oil or to rock like limestone. The carbon can return to the environment as CO2 if the rocks become exposed, or if they get pushed deep underground by the movement of Earth's crust in a process known as plate tectonics. The pressure and heat gradually build until the Earth begins to erupt. Every year, over 100 million tons of carbon dioxide is spewed into the oceans and atmosphere by volcanoes. Acting on timescales of a day to millions of years, the carbon cycle has helped make our planet habitable. But its success depends on life itself. We are how Earth works. If somehow the carbon cycle went wrong, what would Earth be like? The answer is a world away on Venus. Here, the CO2 belching from volcanoes isn't going anywhere. Venus is like a house on fire with the windows forever closed. The cause can be traced in part to those incinerating solar winds. Sheltered from those winds, Earth has kept CO2 levels in balance by absorbing and releasing it in roughly equal amounts. Lately, that balance has been shifting. The amount of carbon dioxide from human activities, including cars, power plants, and factories, now exceeds volcanoes by over 200 times. Much of that is from the burning of oil and coal stored in the earth for millions of years. Since the Industrial Revolution, the amount of CO2 in the atmosphere has increased nearly 40%. With with most of that in the last 50 years. The result? Global temperatures have risen by almost 1 degree Celsius. That's enough to accelerate the melting of vast stores of ice on high mountains and in the polar regions. Since the 1980s, NASA scientists have methodically tracked the Arctic's seasonal changes. They've found it's lost a quarter of the area covered by ice in summer. What's left has also thinned dramatically. That's just the beginning of changes that could transform our world, with some regions getting more rainfall, others drought. Deserts expanding, natural fires becoming more prevalent, wildlife habitat shrinking, polar regions becoming forested. And as the ice melts, it drains into the oceans. By the end of the century, sea levels are now expected to rise as much as 1 meter, inundating coastlines around the world. As our impact on the climate has grown, we've also gained a new perspective on Earth. From space. Technology is allowing us to take stock of the elaborate interconnected climate systems that protect our world and sustain it. Within the fold of wind and water, of time and tectonics, our planet has nurtured another extraordinary participant, life. Today, we are masters of a world revealing itself as more and more wondrous than we ever imagined. Even as we continue to explore its workings, we ask, is our goal to spend Earth or save it? They are eruptions so vast, so earth-shattering, They have changed the history of our planet. Mass extinctions, climate collapse, toxic mayhem. Experience Earth and the solar system at their most extreme in supervolcanoes. The Earth we see around us is a thin disguise. It masks a monster. Beneath the calm, beneath the surface, a fury is building. It's 74,000 years ago on the island of Sumatra, along the eastern rim of the Indian Ocean. All around are signs of the tension rising deep below us. Seismic tremors rattle the landscape. Vents of sulfurous gases have begun to open up across the mountainsides. The clock is ticking down the final moments of a giant's fitful slumber. An immense mass of molten rock is rising to the surface. Cracks in the earth form. Escape routes open. Lava and hot gas begin to pour out. This volcano, known as Toba, has exploded 3 times before in the last million years. This time, it will earn a rare distinction, a supervolcano. Seething from a crater nearly 100 kilometers long, giant columns of smoke and debris fill the skies. Over 14 terrible days, Toba blasts out nearly 3,000 cubic kilometers of ash and rock. 1,000 times more than the Mount St. Helens volcano in the year 1980. It is the largest volcanic eruption the world has known in at least 25 million years. The eruption spreads a thick blanket of ash over an area half the size of Europe. Hanging in the upper atmosphere is a dense layer of soot and smoke, blocking the sun for years to come. Toba's grim aftermath is a global cataclysm. The planet plunges into a volcanic winter. Average temperatures fall by up to 10 degrees Celsius. All that rains is falling ash as drought sets in across the tropics. It does not let up for perhaps 1,000 years. Scientists believe that Toba's wrath was felt as far away as Africa, by our own ancestors. In the dark years immediately following the eruption, their food supplies dwindle. It's an age defined by a dramatic crash in their population. The Toba eruption may have brought the human species perilously close to extinction. What causes a supervolcano? The answer begins with the birth of our planet some 4.5 billion years ago. It happened in a swirl of debris left over from the formation of the sun. Amid the chaos of the early solar system, gravity drew together clumps of rocks and dust. Countless objects collided and fused. Each collision generated heat. Under the barrage of impacts, a fiery young planet formed, molten at first. In time, the impacts decreased. Earth's surface gradually cooled, but its interior stayed hot. To this day, heat energy rises from deep inside the planet, a vivid reminder of the fires that burn within. The heat escapes in part through volcanoes, especially along the outer rim of the Pacific Ocean. Here is the notorious Ring of Fire. To see the furnace that powers its volcanoes, peer inside the planet. The heat moves up through a vast middle region called the mantle. It punches through where Earth's crust is thinnest in the middle of oceans. That causes massive plates that line the surface to push apart. Along the Ring of Fire, these oceanic plates collide with thicker continental plates. They thrust down into the Earth, carrying with them volcanism's secret ingredient, water. Some rocks, when mixed with water, melt more readily. They form a reservoir of magma that can fuel a volcano. It's an elaborate chain of events that Toba took to an extreme. As the molten rock and debris is blasted into the air, the entire volcanic mountain range collapses down, creating an immense cauldron-shaped basin. Water and heat are the agents of change for a world that's still a work in progress. Earth is not the only one. Welcome to Triton, Neptune's otherworldly moon. With surface temperatures at minus 235 degrees Celsius, this is no place for lava to flow. Instead, volcanoes of water ice shower the landscape. On Triton, it's the geysers that qualify as super. They can blast liquid nitrogen at almost 700 kilometers per hour to a height of 8 kilometers above the surface. Some volcanoes on Jupiter's moon Io have plumes of escaping gas that reach 500 kilometers above the surface. If on Earth, they would rise above the International Space Station. What powers Io's eruptions looms on the horizon. Jupiter exerts a massive tug on Io's core, generating heat. Much of it escapes in the largest volcano in the solar system, known as Loki. It may have formed when an impact blew a hole in Io's thin outer crust. There are traces of volcanic activity on Mars, Venus, several moons of Saturn and Jupiter, and in the past, even our own moon. But it's Earth that may bear the deepest scars. The most destructive volcano known in our planet's history took place in what's now Siberian Russia. Wind back the clock to the time of the eruption, 250 million years ago. All of Earth's land masses were joined together in a supercontinent known as Pangaea. It was the end of a spectacular period known as the Permian. That was a time when life on Earth ran riot. Amphibians and early reptiles flourished, including the ancestors of dinosaurs and mammals. Forests and swamps saw an explosion of insect species. Fern plants, dominant for eons, were beginning to give way to conifers and palms. The oceans brimmed with life's bounty as well. Amid vibrant coral reefs, a wide variety of invertebrates and fish inhabited the open water. Here was Earth in all its glory. Then, in the geological blink of an eye, it was over. Up to 70% of all species on land and 90% of marine species disappeared. Ecosystems around the planet collapsed in a mysterious blight called the Great Dying. What happened? Scientists believe that a broad plume of rising magma pushed toward the surface. When volcanic formations like this spread out, their energy dissipates. But imagine if instead that their tentacles rose and exploded as one in a sprawling supervolcano. Here was hell on Earth. A series of small eruptions generated 1,000 times more lava than the Toba volcano. They choked the atmosphere with carbon dioxide and methane gas. Global temperatures soared. The oceans turned acidic, their waters depleted of oxygen. The Earth belched deadly toxins, including high levels of mercury. Through the history of our planet, eruptions on this scale are thankfully rare. Could one happen now? The answer is a secret in plain sight. Visitors to Yellowstone National Park in Wyoming may never suspect they are atop one of the world's largest active volcanoes. Its legacy is written across scenes like this, the fabled Yellowstone River. The heat below softened layers of volcanic rock. Catastrophic flood at the end of the last ice age then gouged out this spectacular canyon. All around, thermal energy is underfoot, like a pressure cooker gathering steam. it escapes in smoldering cauldrons, in spectacular geysers that can blast hundreds of feet into the air. In primeval hot springs laden with sulfur that simmer near the boiling point. We venture to Yellowstone to admire this thermal spectacle. Imagine if we could follow it down to its source. Surface water seeps into the ground, moving through cracks in the underlying rock. A kilometer below, the water enters layers of heated rocks, then shoots back to the surface. Deeper still, 10 kilometers down, are the upper reaches of an immense plume of magma. It's over 100 kilometers wide and 400 kilometers deep. Yellowstone has erupted time and again over the last 18 million years. Several have followed the same tripwire events that triggered Toba, the sudden release of large amounts of magma, the collapse of the land, and the rise of a supervolcano. Yellowstone is overdue. It may not erupt again for hundreds, even thousands of years. Still, scientists are watching for early signs. Earthquakes, rising heat, the restless stirrings of a planet under pressure. Yellowstone's geysers, like Old Faithful, remind us that someday, once again, the planet will vent its rage. Supervolcanoes may be rare, but the fury that fuels them is ever present. If science tells us anything about them, it's that when the next one does erupt, life on this planet will be forever changed. It was the Soviet Union versus the United States. The technological advances of the space race rippled through society. computers, satellites, materials, missiles. But its greatest legacy may not be something we made. Rather, it's a collection of rocks that astronauts picked up off the surface of the moon. They have led to a whole new understanding of Earth's early years and of our moon's mysterious beginnings. It's the brightest object in the night sky. For millennia, the moon has defined the rhythms of life and animated our myths. It has played a central role in our planet's history by stabilizing Earth's rotation about its axis, and with its tides promoting the formation of ocean currents that shape our climate. And yet, within its brilliant light is one of the most vexing questions in all of science. Where did the moon come from? At the dawn of the space age, in the 1950s, there were three competing theories about the moon's origins. One held that it was part of the Earth, cast off by the rapid spin of our planet in its early days. Another saw the moon as a wayward object that floated through our solar system and was captured by Earth's gravity. A third idea held that the moon formed right alongside the Earth. Scientists from the Soviet Union and the United States sought to test these theories with a fleet of unmanned lunar probes, shooting pictures, taking readings, and crashing onto its surface. To settle the question, we needed to go down onto the surface of the moon, to see it with our own eyes, and bring a piece of it back to our labs on Earth. But the quest to obtain samples from the moon was fueled as much by science as by competition between the two nations. The race to space began on October 4th, 1957. When the Soviet Union launched a satellite called Sputnik, higher and faster than anything before it. Sputnik's beep was a wake-up call for the United States. It led to the creation of NASA and a mission to get an American into space. The Soviets then launched Sputnik 2. It was 6 times heavier and had a passenger, a dog named Laika. Surprising the world again, the Soviets launched a spacecraft on April 12, 1961, that carried a man into space. Cosmonaut Yuri Gagarin. From 1957 till 1965, the Soviets routinely bested their American counterparts. To overtake the Russians, President John F. Kennedy had to aim high. He committed the United States to the goal of landing a man on the moon before the end of the decade. Nothing so grand is ever so easy. The Gemini program was set up to build the skills and technologies needed for a successful lunar mission. It had its share of mishaps and failures. The Soviets were working on their own moonshot with the giant N-1 launcher. It had a complex design that included 30 engines on its first stage, all of which had to work flawlessly and in sync. Testing on the different stages of the N-1 started in 1968, followed by 4 full-scale unmanned launches. Meanwhile, the American lunar program pinned its hopes on the mighty Saturn V rocket. The first manned launch of the Saturn V would carry the Apollo 8 capsule to the moon and into lunar orbit. Apollo 8 coasted to the moon and successfully returned. Both nations now had a lunar landing in sight. On July 13, 1969, the Soviets launched Luna 15, the third in a series of robotic craft designed to land on the moon, analyze lunar dirt, and fly samples back to Earth. Apollo 11 blasted off 3 days later. Luna 15 arrived on schedule, but Soviet controllers kept it in orbit to check its onboard systems. On July 20th, 1969, Neil Armstrong and Buzz Aldrin began their descent to the lunar surface. Computer overload alarms caused the Eagle lander to overshoot its designated landing site. Flying above boulders as big as houses and running low on fuel, Armstrong took manual control and searched for a spot to touch down.
More forward, drift into the right level. Count a half. 30 seconds. Contact light. Okay, engine stop. We copy you down, Eagle. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again.
The 2 astronauts were out on the surface about 20 minutes later. Just as the American astronauts completed their first walk, Luna 15 finally began its descent. But within minutes, communications ceased. The thinking is that it crashed into the side of a mountain. Neil Armstrong called stepping onto the moon a giant leap for mankind. But it's what he and other astronauts picked up that may turn out to be Apollo's greatest legacy. On this and 5 subsequent missions, the astronauts entered a world that's frozen in time. In the absence of an atmosphere, the rocks, dirt, and craters held evidence of events dating back nearly to the moon's birth. Meanwhile, as they walked and rambled about, scientists on Earth were taking a fresh look at the lunar surface. They noticed, for example, that some large old craters are surrounded by concentric rings. You can see them in this image of a feature called the Mare Orientale, captured recently by NASA's Lunar Reconnaissance Orbiter. The colors show differences in elevation. Scientists began to suspect that the rings were created when an impactor splashed down on a molten surface. That gave rise to the notion that early in its history, the moon's surface was a vast ocean of magma. When the astronauts arrived, they found relatively light rocks strewn about the surface. They could have been forced to the surface by heavier material that had sunk toward the moon's interior. The rocks contained another important clue to the moon's origins. They were found to be strikingly similar to those on Earth, in part because they share forms of oxygen that scientists regard as blood types for solar system bodies. A striking new theory emerged to explain the evidence. Early in the history of the solar system, the theory holds, Earth shared an orbit with a Mars-sized body called Theia, named for a titan in Greek myth who gave birth to the moon goddess Selene. When its orbit became unstable, it headed in Earth's direction. Theia hit at an oblique angle, causing the Earth to spin faster and debris from both Theia and the Earth to fly into orbit. When the dust settled, the debris began to coalesce in Earth orbit, forming the moon. By then, volatile compounds like water had evaporated. The moon then comes primarily from the mantles of the Earth and Theia. That's why, on the whole, it's lighter or less dense than Earth. From this violent beginning, the moon gradually cooled and the magma that lined its surface hardened into a crust. Yet it was still subject to intense bombardment in the chaotic environment of the early solar system. The Apollo astronauts encountered a secondary effect of all the impacts. Rocks that were formed in the crucible of widespread volcanism. On Earth, volcanic eruptions are often powered by water, heated and pressurized during the movement of immense tectonic plates. Volcanism on the Moon is tied to impacts forceful enough to melt the surface and release material from the hot interior. When this happened, molten rock flowed out in thin, smooth layers that reached far from its source. That's how the Mare regions that cover about 1/6 of the entire lunar surface are thought to have formed. These immense volcanic basins date back to a period of large and violent impacts from 3 to 4 billion years ago. It now appears that impacts had made an even deeper impression. One new study seeks to explain the Moon's lopsided topography. The dark lava basins on the near side and the highlands on the far side. It holds that another much smaller body formed alongside the Moon at the time of its birth, and eventually merged with it. The violence of the merger literally rearranged the Moon's interior, pushing molten magma onto the near side, while adding an extra layer of crust to the far side. Apollo astronauts took the first step in studying the interior of the Moon by installing a network of seismographs. Scientists recently followed up by performing a kind of CAT scan of the Moon. They sent out a pair of spacecraft called GRAIL to orbit the Moon in unison. By measuring subtle changes in the distance between the craft, scientists can discern variations in the Moon's gravity. What they found was that the Moon's gravity is not smooth. Rather, it's pocked with regions that exert an especially strong pull. GRAIL scientists have now linked these regions to dense concentrations of mass deep inside the Moon, and these to large impact sites such as the Mare Orientale. Lunar impacts appear to have left an even more remarkable legacy. In the year 2009, the L-Cross probe arrived at the Moon aboard the Lunar Reconnaissance Orbiter on a collision course with the South Pole. It slammed into a crater. Seconds later, a trailing probe detected a tenuous cloud rising up from the crash site. Readings of this cloud showed that 5.6% of the crater floor consists of water ice. Most likely, it was delivered by comets that crashed into the Moon. It had survived over the eons in craters with steep sides that shield it from the sun. It turns out that may be just the beginning of vast hidden stores of water. Circling the moon repeatedly aboard the Lunar Reconnaissance Orbiter, a Russian-made instrument called LEND has found evidence that hydrogen and perhaps water ice is embedded in lunar soils beyond the polar craters. And now, rocks picked up by the astronauts are telling an even deeper story. Analyzing them with new techniques, several teams of scientists recently found a compound called hydroxyl. It's H2O, but with only one atom of hydrogen. Based on this evidence, scientists estimate there is enough water locked up inside the moon to cover its surface in a layer 1 meter deep. The intimate connection between the Earth and the moon appears to trace back to their earliest times. So far, we've really only scratched the surface of their shared history. The quest to understand that relationship was once part of the feverish competition of the Cold War. A whole new race to the moon is now heating up. This time, fueled by the search for valuable minerals and metals, mining and money. Russia, the United States, China, India, and Japan all have missions in development, including an array of manned missions.
Discovery's engines are now throttling down as the orbiter passes through the area of maximum pressure, reducing the stress.
A number of private missions are also on the drawing boards. What will these missions tell us about our celestial partner and how it formed? Inevitably, the more we learn about the mysterious birth of the moon, the more we'll learn about its mother planet, Earth. Earth is a water planet. Vast interconnected bodies of water, the oceans, cover 71% of its surface. They moderate the global climate. They fuel storms that drench the land and feed the lakes and rivers that sustain us. And now, scientists have detected whole oceans of water hidden in rocks deep inside the planet. How did our world come to be endowed with such a rich bounty? Is Earth the only oasis in space? For as long as we have gazed upon the stars, they have offered few signs that somewhere beyond our solar system are worlds as rich and diverse as our own. Recently, astronomers have been discovering planets at a rapid clip. Using orbiting observatories like NASA's Kepler Space Telescope and sophisticated ground-based telescopes. These alien worlds range from great gas giants many times the size of our Jupiter to rocky, charred remnants that burned when their parent star exploded. Some have wild elliptical orbits. They swing far out into space, then dive in close to the scorching atmospheres of their parent stars. Amid these hostile realms, a few bear hints of water or ice. Ingredients needed to nurture life as we know it. The race to find these Earth-like planets has raised anew the ancient question whether, out in the folds of our galaxy, planets like ours are abundant and life commonplace, or whether Earth is a rare Garden of Eden in a barren universe. We can begin to find out by reaching back into the history of our planet, to the particular circumstances that endowed it with its stores of water. Beyond our solar system, even in the cold blackness of space, our universe is awash in atoms and molecules. They are the raw material of the evolving cosmos. The basic building blocks of stars and planets. In some regions, a nebula may glow with an eerie light of stars. These are places where new stars and solar systems are being born. Thousands of these glowing gaseous clouds are scattered throughout the galaxy. Within their frozen interiors, atoms combine into more complex molecules. Ammonia, methane, carbon monoxide, and water. To astronomers, the presence of water, H2O, is no surprise. Oxygen, the fifth most abundant element in our universe, originates in stars that dominate many nebulae, known as red giants. Deep in their cores, high heat and pressure causes hydrogen and helium atoms to crash together to form heavier atoms like oxygen. When these stars die, they kick oxygen and other elements out into the surrounding region. About 5 billion years ago, within such a rich chemical soup, a medium-sized star, our Sun, was born. Within the swirl of gas and dust flowing into this newborn star, a solar system of planets, moons, asteroids, and comets gradually took shape. Today, you can find water in nearly every corner of our solar system. Pluto and its moon, Charon, are part of a class of small objects orbiting the outskirts of the solar system. They are leftovers from the creation of the planets. Their surfaces are lined with a thick layer of frozen methane and water ice. Further in, the blue planets, Neptune and Uranus, get their color not from water, but from methane clouds that lace their frigid atmospheres. Within them, charged particles circulate in a sea of liquid water, producing electrical currents and magnetic fields. These oceans probably resemble battery acid more than water. Within the folds of Saturn's rings are countless particles of ice. Hovering just above them is the moon Enceladus, with an icy surface that makes it one of the brightest objects in the entire solar system. The Cassini spacecraft detected a jet of water ice shooting out of its south pole. Scientists speculate that it's escaping from a liquid ocean beneath the surface. The largest planet, Jupiter, harbors its own storehouse of water. Though water exists in relatively small amounts in the giant